Uh, it's a great pleasure to have Professor Devabrat Shah here in today's AI4OPT seminar. So Devabrat is a professor of ECS at MIT. He's currently the faculty director of Deshpande Center for Tech Innovation as well. He also co-founded multiple labs and very successful startups. His current research interests include algorithms for causal inference, social data processing, and stochastic networks. His work has been recognized through numerous major awards and prizes, including ACM Sigmetrics Rising Star Award, Inform's Erlang Prize, and Best Paper Awards at IEEE Infocom, Sigmetrics, NeurIPS, Inform's Petroleum Society, MSOM, and
we can stop.
Sigmetrics.
Thank you.
So it's a great pleasure to have you here, Devabrat. So without further ado.
Well, thank you. Thanks, Devankar. Thanks, Shiva, and thanks everyone for having me here. It's a pleasure to be here. Shiva just reminded me that exactly 6 years ago I was here, and so really glad to be back. And thank you for the seminar series, especially for the food, because as everybody knows, if your audience is happy, no matter how terrible talk you give, talk goes well. So thank you. So with that high note, let me get started with the presentation. Again, I know we are a little bit distributed that way, but feel free to stop me at any point of time as I go through the talk. I don't have too many slides I really want to go through. At least there are a few insights that I want to give, and then to the extent I can give you one short proof, I think I'll be very happy. Rest is just complications. This is based on joint work with Abhin Shah, who is a graduate student at MIT in the Department of Electrical Engineering and Computer Science, co-advised by myself and my colleague Greg Warnell. Raz Dwivedi, who is a postdoc with us at MIT and Harvard, now soon to start at Cornell. He also contributed to this work. Title is long. Primarily, it's about trying to do causal inference when confounders are not observed using exponential family modeling. Okay. As I go through the presentation, I'll sort of first motivate what is the style of questions we are thinking about, what is the model itself, what the problem is, and then sort of tell you key results first, and then sort of talk about methods, at least the gist of the method. Okay. Again, please feel free to stop me at any point of time. So with that, let's get started. So thinking of, at some level, a very simple setting, of sequential recommendation system. So as we know, and again, this is a nice caricature to explain that you watch Iron Man. Again, this tells you a little bit about my interest, right? You watch Iron Man, or your recommended Iron Man, you watch it for some amount of time, then your recommended Hulk, and then you say, well, okay. And then your recommended Thor, and you watch it full. Definitely, there's nothing else to watch. And then you recommended Captain America, and you watch for some amount of time, right? So basically what has happened here, a few things. One is you are told something to do because a system, underlying recommendation system or portal believes something about you, is some algorithm. And then sort of what you showed, what expression or what sort of you told me about. So there is some kind of a sequential dependence, some things that I observe and some things I don't observe. And what I would really like to do is that if instead of Iron Man, Hulk, Thor, and Captain America, what if I had showed you Goodfellas, Godfather, ... how would your outcomes would have looked? Okay, that's the style of questions I want to answer. Okay, and just putting a little bit of structure around this question now. As you can tell, these are my sequential outcomes that I'm observing. So you go y1, y2, y3, ... I will assume that that is a high dimensional. Okay, this will become clear as I'll go forward. Then these observations are due to sequential collection of actions or interventions or decisions. And of course, as these things happened, at each time, there were some observed covariates that were there. Like the first time it was was watching at home, maybe watching in the plane and watching on phone, ... whatever that is, okay? So those are the observed covariates. And then there is something about me, about system, about how things are that you have not observed. And that something is actually also impacting all of these things. Now, one might say that, well, that something itself might change over time, might be sequentially dependent, might get impacted by these things as well. I'm not going to go in that generality. I'm going to, for the purpose of this talk, I'm going to start with this as a modeling assumption, okay? So there are type of things that this would sort of faithfully capture, and the type of things this type of model may not faithfully capture. So I just want to make sure that what are the limitations and hopefully strengths. Okay. Again, I've not given you all the details yet. I'm sort of slowly I'll peel the onion, but this is the type of setting I'm looking at. Okay. Taking a step forward. Okay, so what is the setting I'm going to be interested in? Well, since I'm interested in understanding for any individual, what would be the sequential outcome would be if I change the sequence of actions. If I had only one observation, there is one individual, it will be very hard for me to do it. And hence, one way to have a little bit more information is maybe have multiple trajectories like this. So there is a multiple individuals, their trajectories are there under different sequence of actions. Okay, so I'm going to index by small n the set of number of trajectories I have. Okay, and under different sequence of actions for different individuals, I'm going to observe these outcomes. Okay. Again, for each of the individuals, their unobserved z's would be different. So maybe there is a z1 for this individual, zn for this individual. Okay. For each of the individual, in addition to outcome and action, sequentially, I might be observing some covariates as well. And these covariates observed here might be different from what I observed there. Okay. So that's the data, that's the observation I have, that's roughly the setting. And the goal is for that individual, for example, if I change a sequence of recommendations in this case, or for that individual, I change sequence of recommendations in that case. Now, you know, I watch movies with my 8-year-olds. Then sort of this is these are the questions that one is asking. That is, what will be the sequential outcome? Again, I want change covariates and I want change unobserved z. Okay. All right, so that's a high-level goal. Now I want to sort of put a little bit of formalism and then sort of define this a little bit precisely. Yes.
Know the characteristics of each subject, or you just assume the data ID?
Okay, so characteristics of each subject, modeling wise, could be captured in the unobserved z. Suppose hypothetically, you and I know z's and v's and a's and everything. Then outcome y is, let's say, conditional distribution that is same across all individual. Condition on a's, v's, and z's. And I will assume the traditional stable unit treatment value assignment, i.e. that sort of outcomes of individual 1 do not impact outcomes of individual n. The question? I'll come back to that formulation a little bit more precisely again.
You do not know anything about the similarity of two individuals, right?
No, but sort of the hope is that there is something that we can do. Okay, otherwise, so the first challenge here is this, right? There's an unobserved factors create spurious associations, and what I'm going to show you, if you have seen this before, you know it. If you've not seen this before, it's quite interesting. Okay, So if you've seen this before, maybe sort of you can take a pause and enjoy. If you've not seen this before, it's really interesting. And here is, for example, one data set where somebody had captured information saying that how much amount of comedy is there in a content and how much amount of level of engagement that people had. Okay, what one would hope is that if the X's are defined right, then maybe comedy should increase people's engagement, right? But this looks off. And the reason it looks off is because each data point corresponds to an individual who actually expressed her or his engagement level for that piece of content where comedy content was there. Okay. Turns out if I knew what the age of the individual were, and I could sort of quotes and quotes separate them, these are the individuals with a higher age and these are the individuals with lower age, then for each of the age group, we can see that sort of actually there's a right behavior. Okay, that is, as you increase the comedy level, their engagement level also increases. It's just that they're different across ages. So that means that the Z that I was talking about effectively in this context is the age. If I knew the Z, then conditional distribution of outcome, which is engagement level, and action is comedy amount, actually that distribution is different. For Z equals to 50, let's say it's a linear version is this, versus Z equals to 10, the linear version is this. Okay, so really not knowing Z is a challenge. And if in this data set, when you gave me that, somehow miraculously you figured out who are the 10 years old, 20 years old and all that, you will be able to sort of take care of that. And that is basically the challenge we are going to solve, because we will have to solve that problem because we don't know Z's. Okay. The thing here is that there's only one number and that may not help us solve it, but if you have a high dimensional setting, that can help us solve it. And again, it's a very simple classical insight is that if I have two coins, one with bias 0.5, another with bias 0.75, every time I pick one of the coin at random, toss it, and then I show you coin flips, you won't be able to tell whether it's a 0.575 or it's 0.25, 0.75 or it's 0.5, right? Did I got those numbers right? Okay. But then if I instead did the following, I took a coin out, then I tossed it 10 times, then I put it back, tossed it 10 times again. Now you might be able to start saying, well, first 10 was whether it's 0.25 or whether it's 0.75. Okay. And that's basically the type of thing we want to do here. Okay. All right. And of course, users could be heterogeneous. That is, if everybody came from the same age, there's nothing, okay, but people have different ages. Now, when I saw this chart for the first time, it felt bad because I know where I'm going. But that's besides the point. Yes.
So this observation that if there's correlation between some of the explanatory variables and the unobserved factors, that can bias the parameters. That's a traditional topic in linear regression, right?
There's a traditional topic, there's a classical topic in everything, yes.
So what is it that you can do? What enables you to overcome that classical problem? Is it the fact that you have panel data or what?
Yeah, because I have a high dimensional data. I'll make it more precise. Okay, and again, sort of it's captured through that simple example. That is, if I have a mixture of two coins, 0.5 bias, 0.75 bias. If every time I pick a coin and flip it, and then sort of then effectively what you're going to observationally, you will see half of them are heads and half of them are tail. So you won't be able to tell it different from a fair coin. But if instead I picked a coin, tossed it 10 times, same coin, then I put it back, I picked it again, new coin at random. Then what I'm going to see is either in the 10 coin tosses, I'm going to see closer to quarter heads or closer to 3/4 heads. And I will be able to tell you that. Okay. So now,
You know the identity of the respondent or something.
exactly right. So it's the same individual who is giving me a sequence of outcomes. And now the question is that sort of, can I use that to somehow sort of tell you a little bit about your hidden Z that matters for the purpose of the outcome observations. And of course, that's exactly what's happening behind the traditional panel data setting as well. So one of the interesting thing is, which I won't talk here, but if you know the panel data or factor models, there would become a special case of these things. And once one starts thinking from this perspective, and that was actually my original motivation. Once starts thinking from this, then you can go back to the panel data setting, and then you can start playing with all sorts of sequential interventions as well. There's something we're doing, but happy to talk offline. Great question. Thank you. Any other question? I mean, I don't want you guys to not feel loud because Zoom is asking me to stay here. Okay, so just adding a little bit more details. So really, each of these is, of course, sequence, and across sequence, arrows are crossing like this. Okay, so there's a Z's and there's a V's. Okay, there's no structure assumed, or they can be arbitrarily impacting each other. And then they may determine A, sequence of observed intervention, and they, along with A, will determine my outcome. Okay. So that's the mechanistic model that I'm thinking about. And as I mentioned, I'm going to sort of assume that N observations are independent. And for each of the I have these kind of V's, A's, and Y's that I'm observing. And again, sort of, I'm assuming these are high dimensional. Okay. Especially Y's are high dimensional. I mean, A could be a small dimension too, but. All right. So the counterfactual question of interest is that if I keep this unobserved thing fixed, I keep the observed covariates fixed. But if I change from AI to A twiddle I, what will be my outcome? Okay. And more precisely, I'm interested in this conditional distribution. Okay. And through this, effectively, I'm telling you what I already made a precise probabilistic assumption behind the scene, right? Right now, I will sort of make this parametric model because exponential family hasn't entered yet. So I'll move towards that. Okay, and one thing that sort of I want us to remember, because ZIs are not observed, observationally for us, these are N different distributions, because for each individual, there's a different distribution. I have different conditional distribution, and that's what I'm interested in. But of course, if that didn't have anything to do with each other, we'll be in trouble. So now I want to sort of stitch them together somehow. Okay. And as now just a obvious statement that for each individual, there's a separate distribution, and for each distribution, I have exactly one observation. Okay, so here is how we will do. So yes.
So sorry, I try to have an understanding the formulation.
Yes.
So what's exactly the relationship between Z and V? Is it a condition on Vi that distribution of V will be?
Yeah, so I can put out a parametric form, and then maybe sort of we can, okay, let me sort of put it here first. So I don't know Z, but I know that for a given individual I, that Z remains constant. Okay. So in principle, I could think of this distribution of Y given A, fixed Z and fixed V, for ith individual. I can call this as ith distribution of Y given A with this V. Now the question is that how does P1 and P2 and Pn relate to each other? But if you knew the Z precisely, then knew that they relate with each other this way. It's just that I don't know Z yet. Okay. To define this precise form of how Z relates, I will think of this as an exponential family. Okay, and I will use effectively first and second moment. So that means that sort of there are individual terms and cross terms as my sufficient statistics, and I will sort of formulate that in a second.
A related question. So
Yeah.
if you have a separate distribution for every I,
Yes.
then the fact that you don't know ZI or you know VI so on becomes irrelevant, right? The only thing that matters is just you have separate distribution. for
That's
every
correct.
I.
That's correct.
So it only becomes relevant if you want to share something among the different I's.
That's correct. So if, for example, for one individual, I could have run, hypothetically, I could have run, okay, let's suppose all individual I's have same Z, okay? So everybody has same Z and everybody has same V, let's say. Just remove them for a second. Then seeing outcome for an individual is same as they're all coming from the same conditional distribution. And then maybe I can sort of do something with it. But now, because every individual has different Z and every individual has different V, these are becoming different conditional distributions. And now I'll have to figure out how to share information across that. Otherwise, I won't have enough data to sort of do that. All right, so okay, let me put it out all of that and then sort of just parse through this. So as I mentioned a second ago, thinking of modeling this joint distribution as an exponential family using the first and second moments effectively. And the W, which is Z, V, A, and Y, those are the 4 variables. So this is just a linear term, and this is the quadratic term. Okay. That's my belief about how the world behaves. Now one can say, is it really true? Well, you could add higher moments. Some of these things will naturally go. If I just kept first order, then actually we are in a terrible place because we are looking at independent things. So starting with the second moment is a one reasonable place to start. Okay. So let's start with that. And now if I open that up and I look at conditional, nice thing about exponential family, I'm pretty sure if you have played with them, you retain structure, you remain in the same family when you condition. And once you condition that, which is my ith distribution, has this nice form, okay? So these are my outcomes, okay? So there's a nice quadratic form there. And then this is the linear part for outcome, but it's a linear parameter. Actually depends on few things, right? One part has, of course, there's the dependence origin just from Y. There's another part which is because of Z and how Z impacts Y through cross term. Okay, and we don't know this. Okay, and this is the part where how V impacts Y through the cross term. Okay, so we know V, so maybe we can work hard to actually extract this out too. Okay, but we will not be able to extract this out. And when this is messed up with this, potentially we may not be able to extract this out, and we may not even care. Okay, but this, in a sense, changes across I. It is the way we have set the problem. This does not change across I's. Okay, and of course, this doesn't change. So we are trying, what we are going to do eventually, assuming I get through that, eventually is that we'll try to learn things common across distributions, these things, and somehow work hard to extract these things out to the extent we can. Okay, and this part will determine how heterogeneous users can be. If users are too heterogeneous, of course, no method can help. Our methods won't help either. But if somehow users are coming from less heterogeneous classes or the model complexity, we will define it as primarily the metric entropy of that space, then that will determine what is the error we will incur in terms of learning. Okay, so that's where we are going. Just to sort of put this a little better, this part is a parameter that's just multiplying with Y. Okay, and let's call it I dependent. And these parameters, that is this phi, and that phi, those are common. They don't change across I's. So in a sense, now I reparameterize my underlying distribution through these two things. There's what is a common part and what is the part that sort of changes across I. I don't know Z, but I know that this is a different across each I. Okay, and this is the setting I have. So all n units corresponds to, at least conditional distribution correspond to n exponential families with common parts as for cross terms and quadratic terms. And this is different across them. Now, if we take one scenario where all of these are same, okay, that means that all individuals are identical in terms of their unobserved characteristics. This, in a special case of discrete thing, would become like learning Ising model, graphical models. And there's a very nice work by my colleague Guy Bressler, where he had one of the earliest algorithms, which effectively took what was done by Chow Liu for tree to pairwise Markov random fields and generic discrete Markov random fields with binary setting. Is a nice information theoretic algorithm there. It's a greedy algorithm. And then came Clivans et al., where they connected that to kind of logistic regression like algorithms. And then came the Woufre et al., where they connected that from binary setting to higher alphabet settings. We took it to higher alphabet setting to continuous setting with some changes, but that's where you have the same Z, which is just learning an exponential family or exponential family with first order and second order statistics from n samples. If you take other setting where you say, well, I don't have n things, I have only one. So there's a exponential family with just one sample, one high dimensional sample. What can you do? It's like a nice example of this would be, the classical, you're doing linear systems, right? It's like, and because parameters are shared at each time, so even though you have one sample of time, you're able to learn the parameter, right? So what would be a natural extension of that? And there's a beautiful work that came out again from MIT, is Kandiros, a student of Kostas Daskalakis, my colleague. They had a really nice insights where the assumption was that the quadratic or cross-term parameter, they know it. If you know that, then you can learn this part. So related. Now, what we are trying to solve is kind of a mixture of both, or both problems. We don't know the capital theta, and we have to worry with this. And that's what we're going to do. And the way we are going to go about dealing with this is first we'll rip this apart, and then we'll rip this apart one at a time. Now, that's how I will describe as a explanation, but the algorithm just runs in one step. All right. Let me just give me 1 second. So again, just to summarize, we have n exponential families. For each family, there is a common part, which is cross terms or quadratic part, and there is a not common part, which changes across each one of them, which is sort of related to the linear term. And of course, for those things, ideally, what we would like to do is compute conditional expectation. Okay. First, we're going to sort of spend time learning these parameters, and then once we learn the parameter, then they'll tell us sort of what sorts of conditional expectation you can do. For learning parameters, I'll give you a computationally efficient algorithm. But once you know the parameter to compute the mean in the exponential family, in general, it's not easy. So let's assume that you have an oracle that takes parameters as inputs and produces mean and output, and then we can quantify the error there. Okay, so that's what we'll do. Okay, so that's my data. I'll put it through a nice loss function, and then it'll produce this answer. So it's the traditional empirical risk minimization. So the whole point I want to tell you is what this loss function is and how it comes about. Okay, so in remaining maybe 10 to 15 minutes, I'll spend time telling you about that in a simpler setting first. And that's all I want to tell you. Really, everything else is details, and we'll see how far I can get. Any questions? So far, yes, please. Of sufficient statistics, yes. We'll see that briefly, if I did my work right. Yes.
So you assume this exponential family, and then you also show the graphical model. So given Z and V, there's a conditional distribution on A itself. But then now we are saying that we'll not use that A and change the A.
Yes.
So is this, so why is there a distribution on A given Z and V? I would imagine that it should be different.
Yeah, so maybe sort of in typical, you would, in the world of causal inference, you would assume that data is generated that you observe as per some distribution. And that distribution has, I'm saying that our model. Now, when you want to do the causal inference, of course, in the language of, let's say, Perl, you're sort of fixing the A or you're cutting those edges.
Correct. Do.
Yeah.
So you're not doing
So I'm doing do as soon as I go to conditional distribution. Okay, so okay, so let's just do that. So this is the summary result. Of course, lots of precise details are not there, right? But there's a paper on arXiv that will sort of describe that. The type of result one would be able to establish is that if number of observations scale logarithmic in dimension of data, let's say Y's and A's and V's added up, divided by epsilon to power 4, then you can recover this within epsilon error in some norm. And this is better than just 2 norm. Similarly, so that's for joint, and that's for individual parameter. Again, when think of large dimensional, for them, the 2 norm of that error would be no more than maximum of epsilon and that, so not minimum, okay? The maximum of that, if your, let's say, all Z's are same, then M would be log of 1 effectively 0, then epsilon matters. Okay, if observation or if the Z's are a lot more complicated, for example, if there were, is one example, if these Z's were linear combination of k known vectors, S sparse k known vectors, then this would scale like S log k. Okay, and now this is a vector which is a high dimension. Okay, and I'm saying the 2 norm of entire vector. Let's say the vector dimension is p, then normalized error, let's say 1 over square root of p times vector error is S log k divided by square root of p. So it's, while it scales, it's not too bad. It's per entry error on average, at least, is not too bad. Okay, and of course, this would capture all sorts of complexities. Like going back to the world of linear system setting, this complexity would be very minimal because you got effectively one, okay, so one dimensional thing. Right? And then sort of if I assume that I've got a great mean computation engine, the errors from here would propagate to errors there in this form. Okay. Now, one thing I want to point out is that we strongly believe the ideal exponent here should be epsilon to power 2, not 4. We don't know how to improve it. All right, I'll show you one application because that makes it a little bit more precise that at least this result is useful somewhere. So here is a simple setting. Let's say there is no Z. Okay, there are n individuals, and you're collecting survey or whatever that is. Okay, And for half of the individuals, you know all the covariates that matter for your downstream analysis. But half of the individual, you have errors in the covariates, okay, because you couldn't collect it or whatever. Okay. So let's say for half of the individuals, you know this exactly. For other half, you have some error in the measurements, and you want to correct for those measurement errors. Okay, classical imputation problem. I know which ones have error, and I know which ones don't have error. So there's a typo here. Half users have no error, so there is no here missing. Okay. And other half have sparse covariate errors. There's some places where there's errors. Okay. I don't know what the errors are. They're bounded, but I know that there is somewhere. Okay. And now I want to sort of correct for this. I know these guys are good, and I know these guys are not good. Okay, so can apply this algorithm with this model, and it will result into this kind of mean squared error, where mean squared error is scales like this with dimension. Okay, and you'll be able to get for each eye. So at least this provides a different way to do imputation. And okay, I'll leave that there. Yes. Number of users, number of data points I have. For every user, I have one data point, but the data point is not one dimensional. Is there? Let's call it in this language, it's this long, dimension long. So each user is like a sequence of numbers. Okay, those sequence of numbers include the Y's, the A's, and the V's. So you are user 1, your data point 1. For you, I'm going to observe a Y of length 27. For each of those 27 outcomes, I had 27 different intervention. And associated with that, I had 27 different covariates. So effectively, for you, one individual, I observed a vector of length 51. For him, I observed another vector of length 51. For you, there was a Z that was not there, that I didn't observe, which was also maybe length 27 that I did not observe. For him also, I did not observe. Now, in this example, what I'm saying is that forget Y's and A's for a second, forget Z, there's no Z. Okay, all I'm worried about is the V. Okay, and for those V's, I want to sort of recover them. How would I recover them? This is how I would recover them. It does enter here. That's a dimension. Okay. Thank you. Good. So there are sort of constants that are hidden here, as you can tell, and then those constants would sort of depend on the those things. Okay. Yeah, I should have sort of said that I've gotten rid of all the. No, S is the sparsity. So maybe sort of you should treat this less than or equal to with big O notation. Thank you. Yes.
So in one sample, you actually say you have like a sequential structure. So
yeah.
How do you use that as sequential structure?
So the nice thing here, so we're not exploiting that. Let's put it this way. But the nice thing is that wherever my thing was, right? Despite that kind of a dependence, because of the way things are captured in a cross correlation like this, or cross terms like this, right? Once I condition, this is where sort of the dependence on Y is coming. Now, whether this has nice sequentiality or not, I'm not exploiting that. And potentially, maybe there is somewhere where sort of there's a, not maybe this little, but there's a lot of possibility to improve some of these things. For example, in linear systems, when one tries to sort of learn the parameter, one actually exploits that very nicely. We are not doing that well. Mm-hmm.
Is it intuitive to understand like why the dependence is linear in terms of the sparsity?
That is okay. So why is it linear? Okay, so if you have okay, Okay, so if you have S-dimensional space, forget sort of the log K there. If you have S-dimensional space, right, then somehow sort of the complexity must scale with the dimensionality. Now, where S is sort of, okay. All right, I can sort of walk you through precise calculation a little later. Okay, so first what I want to do is that, okay, let's see if I can do this. What I want to do is that I want to sort of tell you about a loss function, which is not exactly maximum likelihood, but it tries to be as good as maximum likelihood, but in some twisted form. Okay? If I were to take maximum likelihood estimator for this thing, here is how it would look like. That is, I've got, okay, so remember this was the exponential family. I'm thinking of theta as this tuple, okay? So pardon me for sort of changing notation here a little. So I've got n observation from an exponential family with some unobserved parameter theta star. The parametric family looks like this. Given these observations, I want to learn theta star. Okay, maximum likelihood would say that sort of compute log likelihood of theta given data, and then find the theta that maximizes this. If I put myself through the usual calculation engine, what it would give me is something like this. That is my log likelihood, because it's a log, and I'm assuming samples are independent, so it's a sum, and then using that formulation in this. Okay, so that's my objective. And if I want to sort of find the best theta, because this is a nice objective, it's a concave in this case, I will do I'll try to sort of compute the gradient, set it to 0. And as I do that, effectively, this is my moment of sufficient statistics under parameter theta. I'm trying to find the parameter theta that matches my empirical moment, okay? And that's what I'm doing, okay? And it is proper because instead of that empirical one, if I sort of actually replace it by, if I have infinite samples, right, then I will replace it by the true moment. And then it will conclude to me that actually I will find under certain regularity condition that indeed my solution would be the original parameter, and hence it's proper. That's what one would call proper, okay? So the nice thing about, nice thing about maximum likelihood is that, as we know, there's a ton of literature, an amazing ton of literature there. It's like a consistent. It has not only consistent, that is, as number of data point n goes to infinity, the estimator converges to theta star. The error between them normalized appropriately converges to Gaussian. That not only it converges to Gaussian, it converges to Gaussian in sort of most interesting way. That is, it's asymptotically efficient. But of course, because in general computing Z is not easy, this is computationally hard. So the question is that can we at least try to achieve these things, but make this nice? That's one way to look at it. And I will tell you another loss function that looks like this. And the claim is that this loss function for exponential family achieves that property. So just to sort of remind ourselves, right? This was our distribution, right? This was the likelihood. If I take the log of it, we had this term. Now I'm doing something weird, right? I'm doing e to power minus. And then, so if this was product, there would be this without a negative sign. Okay. But it's summation and negative sign. So it's like two things change. Because it's like if it's a poor man's view, it says somebody sort of just made a typo, right? And indeed, it's a good typo. It's a nice optimization problem as long as constraints are reasonable on theta. And it avoids computing Z. So the question is that why is it good? And here is the reason why is it good. Okay, so let's look at, this is my empirical thing. In infinite sample limit, this is same as this. Because data is generated as per theta star. Right? this is same as this quantity by definition, because that's my definition. So now let's understand what this thing is. The claim is that this has a minimizer which is same as the KL minimizer of KL divergence between uniform and another, and the distribution from the same parametric family but twisted version. Okay, see, if you had this, effectively you're doing maximum likelihood, but now I have this. Sorry, yeah, you wanted this, yeah. Okay, and that's, so in some sense you're computing maximum likelihood through this, or this minimization, but with respect to the shifted parametric distribution. Okay, it's kind of a little bit of a funny thing going on. Let me walk you through this argument, and that'll be the only proof we'll do because it's one slide. Okay, perfect. So I'm going to argue that these two minimization problem produces the same minimizer, not the actual value, but the solutions are the same. Their arguments are the same. If we start with this one, which is this distribution, just do basic calculation. What you will convince yourself, it's equal to the p theta star, which is the distribution of interest, times this thing that showed up in our loss function, and then expectation of our loss function in denominator. Okay. And now if I try to evaluate this KL, I will say that this is just a formula, because I've replaced this one in denominator by this, and that. So that, and that. Okay. Now, of course, take the log and sums. So log of these two things here, log of this thing here, and then log of this thing with a negative sign here. It's a linear thing. You can take this out and then take expectation of sufficient statistics function over the, let's say, uniform over the set of interest. If you set your sufficient statistics by shifting it appropriately, so that sort of it integrates to 0, which you can, okay, because that's independent of parameter. Then what you have here is that sort of this quantity, the only dependence in this quantity over theta is through this term. That means if you minimize this, is same as minimizing this. And that's why that is true. Once you have that true, what you will get is these two things effectively for free. And then this one, of course, that's by design. But here's an interesting fact that this doesn't get you asymptotic efficiency. There's a nice counterexample for that. So for those who sort of love these kind of things in exponential family, what would be nice is, can we have all these four? Okay. These three come from maximum likelihood without this. These three come from this one without this. It would be nice to have all four. Yeah.
What is asymptotic efficiency? Is it the variance is correct and the variance is minimized?
Asymptotic, yes. Yeah, thank you. It matches the lower bound. Okay.
Sorry, how far is this from the optimum?
We don't know. As in, I don't know. Sort of, there's a sequence of counterexamples we have, but I mean, don't have sort of a some kind of let's say X factor bound. And there's a nice final sample guarantee. And anyways, I think I'm literally getting close to the last few minutes of the talk. So maybe I'll say, roughly speaking, how does one go about establishing finite sample guarantee for this kind of things? One can use the just a traditional concentration inequalities, and realizing that there's a nice, strong Hessian for these kind of loss functions. So there's some work here. There's an interesting connection happens between. So one way to establish this is to identify even whether there's an independent set or not in the graph. Identify certain independent set in the graph, and then over that make this argument. So there's some interesting tricks here. So if you ever want to sort of establish lower bound of Hessian for a distribution like this, there is some things there. The type of assumptions we need, which I did not spell out before, is we want these guys effectively to be bounded, and for theta star to have sparse representation, at least in the generic graphical setting, graphical model setting. Yeah, I'm now sort of going to, sorry, I'm trying to sort of think, what are the slides not to show? Because there's a sequence of layers in which I'm going to walk through the proof of the graphical model, then proof of setting where I'm going to change a few things, and then eventually to the right answer. Let's ignore this for a second. Okay, I think this one was important. So what would happen is, as one goes to the problem that we care about, the method that sort of, roughly speaking, I described when applied to graphical model, or more generally, the error bound that one established to recover this part is somewhat surprisingly and miraculously doesn't have anything to do with the structure of this. So even if this parameter keeps changing across data points, the dependence in error in your recovery only depends on whether this is common shared or not. Okay, and for that reason, one can sort of actually recover the cross terms without problem. And then once you recover this well, to recover these things, for each sample, what you want to do is you want to see some kind of concentration. Again, going back to the linear system example, if you have a mixing chain, then you would have sort of some kind of a concentration across the sample. Something similar that needs to happen here, and there is a very nice argument that the paper in Daskalakis et al. Had to take a generic parameter like this and apply induce effectively Dobrushin-like condition in the state space setting. And that allows one to do sort of appropriate concentration, and then that leads to nice answers. And we simply adopt those methods. To establish lower bounds for this setting, for learning this well, and few other things, certain logs below needs to be established so that we can get something about Hessians. This was something that we wanted to do, and for distributions that are bounded support. And everybody who sort of knows this world really well, the information theorists and statisticians, we asked them. So everybody said, yes, of course, this must be true. And then we said, okay, so tell us the proof. And then sort of, this is one of those ring style thing. Yeah, look at that, look at that, look at that. And finally, we realized nobody wrote down the proof, and then it is work to do the proof. It is not trivial, but it is not that non-trivial either. But it just sort of, so if you will ever come across looking for log sobolos for distributions with bounded support, at least there will be one reference which you can point to. And again, nothing special. We just use Martin's argument. Okay, I definitely sort of have lost you, but hopefully, let me stop here. Hopefully, I sort of give you the gist of the idea. And there are lots of things to do here. I feel that we are just scratching the surface. Thank you.